Okay, hi. In this video, I want to go through these three probability rules, which are in section 6.2 of the book. That's starting on page 152. What do we got here? Yeah, 152 to 158. Okay, so here's a population. We have, so again, this is a drug study, let's say. And in this population, we have 240 people who receive the drug, receive the active agent, and are alert. We have 120 people who got the placebo and are alert, 60 who got the drug and are drowsy, and 80 who got the placebo and are drowsy. Okay, so if you want to, you can pause the video. We're going to need to have a diagram of this population. So if you want to try creating the diagram yourself, put variable treatment at the top, that is, put drug, the values, drug and placebo at the top. And we also need to find the probability for these four values. The probability of selecting someone from this population who is alert, probability of selecting someone, if we select someone at random, probability of selecting someone who is drowsy, probability of selecting someone who got the drug, and probability of selecting someone who got the placebo. Okay, so if you want to try to do both these things, pause the video. Okay, so here we are. Here are our four probabilities. And to get these, you had to just do this division. So we have, let's see here, 500 people. If you added all of these up, we've got 500 people in our population. So probability of selecting someone who is alert is, there are 360 of those people, so 360 out of 500 is 72%. Probability of selecting someone who is drowsy, there are 140 people who are drowsy, so out of 500 that's 28%. Probability of selecting someone who got the drug is, there's 300 of those people out of the 500, so 60%. And the probability for placebo is 0.4. All right, then the diagram, doesn't matter if you have drug and placebo switched or drowsy and alert switched. The important thing is to have drug and placebo at the top of the diagram. So we've got 80% for people who took the drug, who got the drug, 80% are alert, 20% are drowsy. People who got the placebo, 60% are alert, and 40% are drowsy. Okay, so I just made these numbers up. I don't know what this kind of drug this would be. That I guess makes you slightly more alert than people who got the placebo. But anyway, next, what we want to get to is answering a question like this one. What is the probability of selecting someone from this population who is alert or drowsy? Okay, so we want to figure out the probability for of selecting someone who is alert or drowsy. So for that we need the special disjunction rule. And if you look in section 6.2, that rule is probability of A or B where A and B are exclusive. Okay, I think exclusive, mutually exclusive is defined, if I'm not mistaken, on page 132, back in chapter 5. So when A and B are mutually exclusive, which means having one of those values prohibits an individual from having the other one. So when that's the case, then we find the probability for A or B by taking the probability for A and adding it to the probability for B. Okay, so alert and drowsy are mutually exclusive. If someone is alert, then they can't be drowsy, just by the way things are defined in our model of a population here. So, okay, so probability of being alert plus the probability of being drowsy. Alert is 0.72, drowsy is 0.28. 0.72 plus 0.28 is going to give us 100%. which of course is what we expect because not only are alert and drowsy mutually exclusive, but they're also exhaustive, which is also defined on page 132, which means that in our population, or the way that our variable treatment is defined, everyone in this population has to have either gotten the drug or gotten the placebo. Those two exhaust the possibilities. So consequently, if we select someone at random from this population, there's going to be a 100% chance that they will have one or the other of these two values, alert or drowsy. Okay, so 100%, that one's pretty easy when you're just using we just have two values for your variable. Okay, next, question 2. What is the probability of selecting someone from this population who got the drug and is alert? So for this one, okay, so the probability for drug and alert, for this we need to use the general conjunction rule. And if we look in section 6.2, then we see that the rule is probability of A and B is probability of A times the probability of B given A. Okay, so this is, of course, a conditional probability, which is defined on page 154. You should read that, and I'll explain how to get it for this particular case. But the main thing I want to do here is just get through this rule. So we're using the general conjunction rule here because our variables are associated. Okay, so recall we can tell that treatment and whatever we want to call the variable that we have here on the side, alertness level or something, these two variables are associated because these proportions are, we can tell that they're associated because these proportions are different, 20 and 40, 80 and 60. If these two at the bottom are the same, and these, which would mean these two at the top are also the same, then the variables would be independent. Okay, but they're not. So our variables are associated. So we use the general conjunction rule to find probability of selecting someone from this population who got the drug and is alert. Okay, so now for our particular question here, probability for drug and alert is probability of selecting someone who got the drug times probability of selecting someone who is alert given that they got the drug. Okay, so one question is, how do we find this probability, the probability of selecting someone who is alert given that they got the drug? I'll show you that in 1 second. But we said the probability for just the drug itself is 0.6. So we have 0.6 times. Okay, so there are different ways to find this probability, this conditional probability. The easiest one, especially when you have the diagram already drawn, which we do, is to look at the diagram. Okay, so what we want to consider is, given that someone got the drug, that is, given that someone's in this part of the population, this half of the or this 3/5 of the population, this part of the population, given that someone's over here, what's the probability that that person is, what do we have for, alert. Okay, so, and that's easy to see. If they're on this side of the population, then there's an 80% chance that they're alert, 20% chance that they're drowsy. Okay, but the 80 is what we want. Okay, so 0.6 times 0.8 is going to be 48%. So if we select someone at random from this population, there's a 48% chance that they got the drug and are alert. Okay, good.